Hi everyone, today in this lecture I want to talk about low pass and high pass filters. You're going to see how we can design low pass or high pass filter and how we can detect or how we can figure out a specific circuit type. So let's assume that we have a circuit. We want to see how we can determine what is the type of circuit, if it's acting like a low pass or high pass filter. But before talking about low pass and high pass filter specifically, I want to talk about frequency response of individual circuit elements. So I want to see how different elements react when we change the frequency of the element. So what I would like to look at right now is the frequency response of individual circuit elements. Okay, so I'm gonna start with resistors and then capacitors and finally inductors. And I want to see how they act in different frequency. So if I'm focusing on low frequency or high frequency, what are the impedances of these elements in the circuit and how they act in the circuit. So if I have a resistor, we know that the impedance of the resistor is just R, and the impedance is independent of frequency. So it really doesn't matter if we are talking about low pass or high pass frequency, it's always equal to R. So the impedance of the element is always equal to R. Let's say the magnitude of the impedance. If you're talking about capacitor, the capacitor can be modeled by 1 over JC omega. So as you can see, if we are talking about low frequency, it means that omega is close to 0, and 1 over a number close to 0 is infinity. So the impedance is infinity, and it means that the circuit acts like an open circuit. And if frequency is very high, so in high frequency, this omega, if omega is high, then we can assume that 1 over a big number is close to 0, so the impedance is close to 0 here, and we can consider it as a short circuit. Short circuit means that we have a wire which has very, very negligible impedance. And open circuit means that we have a high impedance that we can assume that the current cannot go through, so the impedance is about infinity. Now let's see what we have for inductor. For inductor, we show the impedance by JL omega. So you can see if frequency is low, then JL omega is a very small number. So if omega approaches to 0, it means that the impedance also approaches to 0. So this time we can model our inductor by short circuit because its impedance is very close to 0. And if our frequency is a high frequency, then in higher frequency, as omega approaches to infinity, our impedance also approaches infinity, and we can model the inductor by an open circuit in this scenario. Now let me show you how the magnitude of the impedance looks like in different frequencies. So if I'm working with inductor, it's a linear relationship between the impedance and the frequency. So it's going to be something like this. So if I'm focusing on very low frequencies, I have an impedance close to 0, and in frequency approaching to infinity, I have a very, very high impedance. For the capacitor, it's the opposite. If I'm close to 0, then I have a very big number for my impedance, and as it goes to infinity, it reaches to 0. So for capacitor, it's going to be something like this. So this is for C, and this is for L. So what you can see here is the frequency response of each individual element in the circuit. Now, knowing this knowledge, it's easier to analyze circuit and see how they react when different signals are added to the circuit with different frequencies.